Welcome back to G Fun Facts Online. Today, we are skipping the preamble because the topic we are diving into is arguably the most critical industrial shift of the 21st century. We are looking at a scenario that is no longer science fiction. We are talking about the year 2026 and the phenomenon known as the magnet crisis. Imagine for a moment that the year 2026 has arrived. There is a silence screaming across the global supply chain. It is not the silence of peace, but the silence of stalled assembly lines in Detroit, Stuttgart, and Tokyo. A term that was once whispered in geological conferences has kicked down the front door of the global economy. This is the story of how the world ran out of the magnets that power the future, and the radical science being used to resurrect them. For decades, humanity has sprinted toward a green future, powered by electric vehicles and wind turbines, assuming the materials to build them would simply be there. We built a civilization hungry for neodymium, praseodymium, dysprosium, and terbium. These are the vitamins of modern industry. We do not need massive amounts of them, compared to steel or aluminum, but without them, the body fails. Without these rare earth elements, an electric car is just a heavy golf cart, and a wind turbine is merely a lawn ornament. The modern world is built on the physics of the 4F electron shell, and right now, that shell is locked behind a geopolitical wall. To understand the solution, we must first autopsy the problem. The magnet crisis of the mid-2020s was a mathematical certainty ignored for too long. For 30 years, the West was asleep at the wheel, while Beijing built a masterpiece of vertical integration. By 2024, China controlled roughly 70% of global extraction, 90% of refining capability, and over 92% of the world's sintered neodymium iron-boron magnet production. But the real chokehold was on the heavy rare earths, specifically dysprosium and terbium. These are the heat shields. A standard neodymium magnet loses its magnetism at around 80 degrees Celsius. An EV motor runs much hotter than that. Adding small amounts of dysprosium allows the magnet to function at 200 degrees. For these specific elements, China's control hit 99.9%. When export controls tightened in late 2024 and 2025, the shockwaves were immediate. Prices for dysprosium spiked nearly 170% in weeks. Western automakers found their order books full, but their supply chains empty. This brings us to the core of today's deep dive, the linear trap versus the circular escape. The traditional linear economy for rare earths is a suicide pact. The process involves digging up massive amounts of ore, which is often radioactive, using thousands of tons of acid to refine it, manufacturing the magnet, using it, and then shredding the car at the end of its life, losing the magnet forever in the steel scrap. Before 2024, less than 1% of rare earth magnets were recycled. We were literally throwing gold and dysprosium into the trash. But within this crisis lies the seed of an industrial revolution more profound than the transition to steam or silicon. This is the birth of the circular economy for rare earths. The mine of the future is not in the ground, it is in the scrapyard. If we can recover the magnets from the millions of EVs and hard drives reaching end of life, we can bypass the mine, the radioactive tailings, and the geopolitical chokehold entirely. However, recycling a rare earth magnet is not like recycling an aluminum can. You cannot just melt it down. If you melt a neodymium magnet, the oxygen reacts with the neodymium, destroying its magnetic properties instantly. You are left with expensive, useless slag. To solve this, scientists have developed 3 categories of resurrection technologies, and understanding how they work is key to understanding the future of manufacturing. The first and most elegant method is short-loop recycling, often called hydrogen decrepitation. This is championed by companies like Hypromag. It is essentially a magic trick. You take a used hard drive or motor assembly and expose it to hydrogen gas at low pressure. The hydrogen atoms are small enough to burrow into the crystal lattice of the magnet. They react with the neodymium-rich grain boundaries, causing the magnet to expand and crumble into a fine, demagnetized powder. The magnet effectively disintegrates away from the steel casing and copper wiring. You do not need to unscrew anything. The powder falls off, is sieved, and can be pressed directly into a new magnet. This process uses 88% less energy than mining and requires almost no toxic chemicals. It is magnet-to-magnet recycling. But what if the magnets are too corroded or glued in for hydrogen to work? That is where medium-loop recycling comes in, a method perfected by Nissan and Waseda University. This is pyrometallurgy, or the high-heat solution. They melt the entire motor rotor at 400 degrees Celsius, but they add a specific borate-based flux. This flux acts like a magnet sponge. As the iron melts, the flux chemically binds to the rare earths and floats them to the top like cream on milk. This allows them to recover 98% of the rare earths without needing to manually disassemble the motor, which is a game changer for the millions of EV motors that were never designed to be taken apart. Finally, there's long-loop recycling, or hydrometallurgy. This is the chemical bath method used by companies like Solvay and Cyclic Materials. You shred the product, dissolve the magnetic fraction in acid, and use solvent extraction to separate the elements back into pure oxides. While it uses more chemicals and energy, It produces virgin-grade material, meaning you can turn an old hard drive magnet into a brand new wind turbine magnet with zero loss of quality. Speaking of hard drives and wind turbines, the geography of resources is shifting. We are entering the era of urban mining. In 2026, the richest rare earth deposits are not in China, but in the data centers of California and the scrapyards of Japan. Every data center cycles through hard drives every 3 to 5 years. Inside the voice coil motor of every drive sits a chunky, high-grade magnet. A hyperscale data center might discard 100,000 drives a month. To handle this, companies like Hitachi and Google have deployed automated disassembly lines. Hitachi's robots can punch the magnets out of hard drives at a rate of 100 per hour, compared to just 12 per hour by human hand. On the other end of the scale, we have the tsunami of wind turbine waste. The first generation of offshore wind farms is coming down. A single 6-megawatt direct drive turbine can contain 4 tons of rare earth magnets. You cannot put a wind turbine in a shredder. These magnets are dangerously powerful, enough to crush a human hand instantly. The solution being deployed now involves on-site demagnetization, using thermal induction blankets to heat the generator housing to 350 degrees Celsius, killing the magnetic field before the turbine is even dismantled. But all this technology is useless if we cannot get the magnet out. This brings us to design for disassembly. For 20 years, engineers glued magnets into motors with epoxy resin, effectively welding them in place. They designed for durability, not recyclability. Apple has been a pioneer in changing this. They realized that if you want to recycle, you must control the robot and the phone design. They built Daisy, a robot that disassembles 23 models of iPhone. Then came Dave, a robot module focusing solely on the Taptic engine to recover rare earths and tungsten. And now there is Taz, a shredder with a brain that uses new technology to liberate magnet-containing modules without shattering the brittle material. The automotive industry is catching up. By 2025, automakers like BMW and Ford realized that gluing magnets was a liability. Newer motor designs use canned rotors, where magnets are slid into slots and sealed with a mechanical lid rather than glue. This allows a recycler to simply pop the lid and slide the magnets out. We are also seeing the concept of the zip tie motor, where the housing is held together by tension bands rather than permanent welds, allowing for robotic disassembly in 5 minutes. This shift is not just environmentalism, it is hard-nosed realpolitik. The circular economy is a national security strategy. The US and EU are realizing that if they can recycle 50% of their annual demand, they cut their geopolitical vulnerability to China by half. The EU Critical Raw Materials Act now mandates that by 2030, 15% of annual consumption must come from recycling. We are also seeing the rollout of the MagPass, a digital product passport. By scanning a QR code on an EV motor, a recycler knows exactly what chemical composition the magnets inside have, such as the specific grade of neodymium and the percentage of dysprosium. Japan is currently the leader in this domain. Having no natural resources, they have treated scrap as a strategic asset for decades. Companies like Hitachi and Panasonic turned the Japanese islands into a closed-loop fortress, where rare earths circulate endlessly within the domestic economy. Looking forward to 2030 and beyond, 3 trends will define the resolution of the magnet crisis. First, the rise of the magnet-free motor. Nissan's externally excited synchronous motor replaces permanent magnets with copper coils. It is slightly larger, but it frees the automaker from the dysprosium tether. Tesla is also exploring motors using ferrite, or iron rust, instead of neodymium. Second is biological mining. Labs are testing bioleaching, where vats of specialized bacteria are fed crushed electronic waste. These bacteria produce organic acids that naturally dissolve rare earth elements, leaving the rest of the metal untouched. It is slow but green and cheap. Finally, we are moving toward a service model. By 2035, you might not own the magnets in your car. A chemical company like Solvay might lease the magnetic function to Ford. When the car dies, the chemical company legally owns the magnets and comes to collect them, ensuring 100% collection rates. The magnet crisis of 2026 is a painful wake-up call, but it is also a graduation test for industrial civilization. We are learning that on a finite planet, the only infinite resource is ingenuity. We are moving from an age of extraction, where we brute force value from the earth, to an age of circulation, where we maintain value through intelligence, design, and care. The rare earth elements that power our green transition are too precious to be used once. They must be the immortal blood of our new economy, flowing from wind turbine to EV to robot and back again, endlessly. The crisis is here. The mines are tapped out. The only way forward is round. Thanks for listening to G Fun Facts Online.